Now let's start Fabry interferometer. This is exactly the same situation that we have talked about in multiple beam interference. This is same two parallel plates, but we are going to call it an interferometer. We'll see how, why. And there is also, sometimes it's called Etalon. And we'll see as we go on. And it's a very old instrument. It's 1899, Fabry and Perot. They have used this device, and it can be used to measure wavelengths. That's why it's called interferometer with a high precision. It is extreme high precision. That's the very important thing. And also because of the, as I said, the flatness requirement for the plates, it's a very expensive instrument. And therefore, because of its high resolution, can be used to study the fine structure of spectral lines. Okay. What is it? It's two optically flat, partially reflecting plates of glass or quartz or any other transmitting material that you may like, with the reflecting surfaces accurately parallel. So again, it's important because since we are talking about optical wavelengths, lambda is of the order of, let's say, a few hundred nanometers, and therefore any deviations from the parallelism and also flatness is going to affect the performance of the instrument. That's why we call it. We want a flat, accurately parallel. So this is the instrument. See, we have two plates, plate 1, plate 2 here. Light going in. These two plates are separated by two spacers, and it can be hard spacers, like any piece of material that can be used there. It is fixed. It can be fixed or it can be used for scanning this, varying the spacing between them. And okay, this is basically, if you have a fixed spacer, it is called an Etalon. And this is the case of a broad source being used, and when it's used as an instrument, you use a collimating lens to make the lenses lights parallel. Then you have a focusing lens where this will image the fringes to the screen here, and that's what you may get. This is a central fringe. Then okay, the thickness goes on decreasing, and the spacing between them goes on decreasing, or in other words, the width of dark and bright fringes will decrease as we go away from the center of the pattern. And these are real images. You can see them on the screen. Okay, that's what it can be visually observed. And any given ring, it represents a constant value of theta, and therefore theta is the angle at which this light rays goes in. Okay, this was 2 theta, and that's the angle of it. And therefore we also call it fringes of equal inclination. These are Fabry-Perot interferometer. Fringes are of equal inclination. Now this is for a fixed spacer. It is called an Etalon. We use it in many places. Then if you're using a scanning method, you can do the scanning uh, method for the interferometer. You can use a point source, or you can use a pinhole somewhere here. Source is placed so that only one spot, center of the ring system, appears at the exit from the plane. That's when it is used as the interferometer. How can you vary the phase? You can vary the phase by adjusting the spacing here. And instead of a solid piece of material as spacer, if you use a piezo material, for example, and apply some voltages across across the two surfaces. Okay, let's say we know that if you apply voltages across these two faces, it's going to expand in this direction, and if you give to both, then the spacing or the spacer can become larger or smaller. That means you can adjust the spacing. That's the sort of resolution that we will need for adjusting Etalon. And therefore, in the case of an interferometer, we will use a point source and a collimating lens, and it goes through, and we use a pinhole so that over the whole rings that's going to form here, only the bright, the center spot will appear on the slit. You can make the slit as small as possible, and then it is detected using an optical detector. Usually, a photomultiplier tube is a very good detector, and also maybe you can use an avalanche photodiode or any photodiodes, which is sensitive enough to detect low light levels. Then the signal is amplified and recorded, and this is one of those recordings shown here. You can, as you vary the spacing between the two plates, that's the variable, the spacing between the plate. That's or you can vary the refractive index inside the medium. What it means is, if you can vary the pressure, that will vary slightly the refractive index of the material, and therefore, or you can input gas, high pressure gas, slightly over 1 atmosphere, then it can change the refractive index. But that method will have various other issues to solve, and also usually you can change the spacing using a piece of material. That is more often employed. By changing that, you can get the spectrum recorded at the output of the interferometer. Now, the output graph is a plot of the area function, 1 plus f times delta. Remember that delta is a function of lambda, and therefore we can see that it can be scanned with wavelength also. There are certain things, certain terms that we should be familiar when we use Fabry-Perot spectrometer, and that is one is the free spectral range. Free spectral range of a Fabry-Perot interferometer, it is defined as the separation between adjacent orders of interference. We have seen that in the initial plot, that is, if you have delta plotted against intensity, this is what we have seen. This is some value for delta, and this is some value for delta 2, and we know that this is delta 1 minus delta 2 is 2 pi. This separation is 2 pi. Now, that's what I have written here. Delta n plus 1 minus delta n is equal to 2 pi. Now you can convert that into in terms of frequency, and this is because we know that delta is 4 pi lambda 0, 4 pi over lambda 0 ending cos theta, and delta is the sum of delta and delta plus r, delta plus delta r, and if you use that, this will become pi c by nd cos theta. Or in terms of frequency, this is c by 2 nd, because this is omega equals 2 pi nu, and therefore c for small values of theta, which is often the case, this is c over 2 nd. Therefore, free spectral range or delta n, mu n plus 1 minus mu n. What does it mean? This is one wavelength for given theta, and this is another frequency. Mu n plus 1 mu n. That difference is c over 2. That you can vary by adjusting the distance between the plates or the angle, but that's not going to be linear. But this is going to be linear and inversely proportional, and therefore the idea is to use small theta so that cos theta is 1. Then change d by some means with let's say cos, what is that? Some piezoelectric material or air pressure, whatever is convenient, and you can use that, and therefore you can increase or decrease this separation. In other words, you can adjust the resolution of the instrument also. Now, resolution of Fabry Perot interferometer. How do you define resolution? You may have, you may know Rayleigh criterion of optical resolution, but here we use some other method, criterion called Taylor criterion. It's also easy to remember. We'll see that. For that, what we are trying to do is to resolve two close frequencies, omega and omega prime. Okay, that is the case. If there are no two frequencies, you don't talk about resolution, because you don't need. Intensity distribution is superposition of two fringe systems, and for simplicity we assume equal intensity, and also to apply Taylor criterion we use equal intensity for the two frequencies, for the sake of the definition of the resolution. Now, what have we plotted here? For each frequency, we will have an area function to be plotted, 1 over 1 plus f sine square delta. Delta, that is 1, and for the other one, it will be 1 plus f sine square delta prime. I use prime for the omega prime. This is frequency omega, and this is for frequency omega prime. And if you look at this, this green, I have marked it as for omega. This green, uh, yellow marked it for omega prime. But when you input both frequencies, what we measure is the sum. If you add these two waves together, this is the red line is what you are going to get. Okay, it's not exactly because I was doing it by hand. I have some drawings downstairs which I have computed using, calculated using origin. Then it will be clear. Okay, we'll go to that when explaining Taylor criteria. And this is what the sum will look like. And therefore, based on this, whether we can see these two humps in the actually measured spectrum, we decide whether the system is resolved. Or the resolution is determined by the parameters that the system has to resolve these two lines. Sometimes you may be able to resolve this line. Sometimes it may have to be some larger frequencies separation between omega and omega prime. Sometimes if you have a better spectrometer, you can resolve a closer line, and that's what we're going to see. Okay, this is the total intensity is IT I0 plus. Okay, these two values. As I said, these two you add area functions for omega and omega prime. F has the usual meaning, and delta has the usual meaning. 2 omega d. Delta prime. These are the values that we have used. Now, we will say that if set to be resolved if there is a dip in the intensity curve. That's what I explained now. But how deep should it be? Should be the you should have some criteria, and that is Taylor criteria. Okay, I'll first read the statement. This is two equal lines, I mean spectral lines, are considered to be resolved if the individual curves cross at the half intensity point. Okay, that's important. Individual curves cross at the half intensity point, so that the total intensity at the saddle point is the point in midpoint, is equal to the maximum intensity of either line. Okay. What is the maximum intensity of either? Okay, let's say the normalized intensity is 1. Or that is the maximum value for a what is the maximum value for an area function? Is this one, and that times I0 will give you the maximum intensity. Okay, let's go down and see. Here I have, okay, these are two Gaussians. Normally in spectral lines are not always Gaussian. Sometimes it can be, because if there is some Doppler rounding, etc., it could become a Gaussian. Anyway, for the ease of calculation, I have used two Gaussians. One is for omega, and this is, let's say the red one is omega prime, and the black one is omega, and this is the sum. Okay, how do you sum? You take the value of W and the value for the other one, omega prime, and then you add. Here omega prime is 0, and therefore the difference becomes appreciable only over here Then you have dip at the center. It's a tiny dip, but it doesn't come under the definition of. The one thing that these are the individual spectral lines. These two are the individual spectral lines that we were talking about. Okay, what was the criteria one? Individual curves cross at the half intensity point. It doesn't cross at the half intensity. The half intensity for this guy is here. This is 0.5. This is 0.5. The maximum intensity is 1. Therefore, it's crossing just above the maximum intensity point. And therefore, that criterion, Taylor criterion, is not satisfied. And also, what was the second one? So that the total intensity at the saddle point, I call this as the saddle point. At the saddle point is equal to the maximum intensity of either line alone. Maximum intensity of this line is 1, this line is 1, but this saddle point is above 1. And therefore, the criterion is not satisfied. But look at this picture. This is exactly at halfway point. This is 0.5, 0.5 here. And the intensity at the saddle point is equal to 1, or the intensity at this point. 1 is because I have used the the area function, but here intensity is going to be I0. Here the intensity is going to be I0. Here the intensity is going to be I0, and therefore the condition is that the individual spectral lines cross at half intensity point, and also the peak intensity, maximum intensity, or the intensity at the saddle point is equal to the intensity of either line alone. That's assuming the two lines have the same intensity. Now this is another situation where it is better resolved, saddle point is lower, and if it is well resolved, the saddle point will go to 0. But this is the definition of resolution according to Taylor. The two lines are said to be resolved if this happens. Therefore, in this case, it is not said to be resolved. Here, it is said to be resolved. Okay. At the saddle point, let's now go on further to see to find expressions for resolution. At the saddle point, what did I say? This is intensity is the sum of the intensities from both spectral lines. This is I0 times this thing is the intensity of the first line. This is the intensity of the second at the saddle point. Here, this is delta, and this is delta prime, where it peaks, where the second one peaks. Okay, this slightly above. This is delta prime. This is delta, and the saddle point is midway between them. That is delta minus delta prime over 2 is saddle. That's what we have used here. Instead of delta, we have used delta. That will make the whole equation delta minus delta prime over 4. Okay, that's what it is. And that intensity at the saddle point is equal to I0 according to Taylor criterion. And I0 will cancel out. I0 and I0 will cancel out, and therefore the condition becomes at the saddle point delta minus delta prime is 2 over square root of. Again, course delta minus delta prime is 1. And okay, this sin theta becomes theta, and sin square theta becomes theta square. F goes to the other side, and therefore 4 over square root of f, and that is f was, what was f? 4r over 1 minus r square, and that is, if you substitute that, this is what you are going to get. Now it's useful to do that in terms of angular frequency, and angular frequency is for, okay, again we use where is delta. Delta was, again you have derived this expression before, 2 omega d over c, 2 omega prime d over c, and that will be 2 times this thing. For delta omega, separation or the minimum frequency that you can separate using an instrument, using a Fabry Perot Etalon, will be c over d 1 minus r over square. And resolution, that's the resolution width, or it is also the fringe width, half inch, and it depends on the spacing and the reflectivity of the plates. Okay, that is resolution. You have seen what was the first one, resolution. That is the resolution. Then, according to Taylor criterion, this is the width of, or the minimum width that you can resolve using a Fabry Perot Etalon with the spacing d and reflectivity r. If you want to change the resolution, then what you will do is to change either d or r. Now there is something called reflecting finesse. It is the ratio of the free spectral range to the fringe width. Okay, that is delta n plus 1 minus delta n. What is that? This was the delta along x-axis, and this is intensity, and this is delta n, and this is going to be delta n plus 1, the first figure that you are seeing, divided by this thing here, delta minus delta prime, and that is given by, okay, if you substitute for 4, that is the reflecting finesse represented by the curly f. But you may have heard a lot about resolving power. Even for grating, you may have seen, you may have measured it during your undergraduate classes, and that is reciprocal of fractional resolution. Fractional resolution is delta omega over omega, and the reciprocal of that will give you the resolving power. Okay, this is what it is, omega delta omega, or in terms of angular frequency it is like this. For frequency it is omega or delta omega, and for wavelength it is lambda over delta lambda. And that's the general definition of resolving power. Doesn't have to be a Fabry Perot interferometer. In general, that's how you define the resolving power. Okay, now for what would be the resolving power for the Fabry Perot. that is omega or delta omega. You know what delta omega is. You have just seen it. Then you know what omega is. 2 pi c over lambda is omega. Then or 2 pi nu. Then this is what you get, 2d by lambda times pi square root of r divided by r, if you substitute all these things. And that is n times the reflecting fields that we have seen. F is the reflecting finesse there. Now, let's, okay, we know that this is 2n pi 2d lambda, 2d over lambda. Okay, if you cancel this and this becomes 2d, and this becomes 1 for small theta, and okay, if you just ignore for a minute, then 2d lambda is equal to n, and therefore this is going to be your resolving power. N times what is n? It is the order of the interference, and this is r is the reflectivity, and therefore the resolving power is a function of the order of interference and the reflectance. Resolving power can be increased by increasing the order of interference. N can be increased by increasing the number of separation, because n is this one. It depends on the mirror separation d linearly, and with the higher resolving power, the free spectral range decreases. En minus. Increase d, you get better resolution or resolving power, but the free spectral range varies inversely at d, and therefore it decreases. And therefore it's a compromise between resolving power and free spectral range. How far, how much, how long in frequency domain you want to observe, and also resolution. If you increase the resolution too high, then the frequency range over which you can look at will be, and that's it's a compromise. And resolving power typically is about a million is the resolving power. If you remember, for grating it was like a few. Remember what it was? It was a few hundred, a few thousand, I think, few thousand. I'm not sure. Maybe you have to go and look for it. For a given d Rp, resolving power in principle can be increased by choosing R closer and closer to 1. 1 is the maximum, and in that case you can also have absorption, and in order to avoid absorption we can use multi-layer dielectric films like as mirrors, and these are better than some of the conventional metal films in terms of absorption. Okay, and all these will make Fabry Perot Interferometer a very high resolution instrument for spectroscopy and hyperfine structure of spectral lines, measure wavelength with high precision, etc. Okay, and with that I think I can stop for now. If you have any clarifications that's needed, you can talk.